example of graphical approach to summing them, because I'm going to ask you both ways for sure on the test. And the algebraic approach is what I went over this morning, what I've gone over the last few days, and in a lot of free periods with a lot of you. And online, I put like 4 more examples under videos from class with all algebraic approaches. So to kind of counter that, let's look at a graphical approach for this. So if you were given a graph and you were told that vector A on the graph, that vector A looks like this, and here's vector B. Let's say vector B looks like this. And let's say that we're told that this is 2, this is 7, this is 1, this is 3. Here, this is 2. This is, let's say, 7, not drawn to scale, please. And then finally, this is, let's say, 3. And this is over here, 9. Okay, let's say we're given those, and I've noticed I'm giving you the values where the endpoints of the arrows are. So we're given vector A and vector B here, and we're asked to sum vector A and B together using a graphical approach only, not using the table method. And why can't you use the table method here right away? What else do you need if you want to use the table method? You need some things.
You need like angles.
You need angles, and you need the length of the vector. You don't have either of those. You could find the length of this vector by using the distance formula or Pythagorean theorem by finishing the triangle. That's fine. But if you're taking a graphical approach, don't find the angle. Don't find the resultant. Just literally think about slope and think about counting for this part. Well, what I'm saying is I don't even want vector A. I just want you to think about the x and the y components of each piece only. Good. So this would be a 5 increase on this side, and this would be an increase of 2. Rise and run are good. Those words work. But we're not actually finding slope, right? But just so we're aware of what we're doing. So this is like 2 in the horizontal component and 5 in the vertical component. And then the next one is down 6, right? Down 6 in the y, and then over 5 in the x. So notice my signs. My signs are like my components. When you guys did this with the vector table, this is what you were doing. You were finding the components. But because it's given on an xy axis, it's really easy to find the components just by actually looking. And if I give you grid lines, you do the same thing. You're literally going to count the boxes. Oh, this goes over 2 boxes. This goes up 5 boxes, whatever it may be. So now, if I want to find the sum of vectors A and B, calling this vector A and this vector B over here, I start with vector A, and it can be anywhere. Doesn't matter what the point is. Start right here for now. Okay, that dot at the bottom. I'm going to go over 2 and up 5, so to make it better to scale, right? I'm going to go over 2 and up 5. Then from the end of vector A, I'm going to just simply attach vector B. I'm going to attach vector B. To do that, I'm going to go to the right 5 and down 6. So down 6 is going to bring me below where I started, right? Look where I started. I started here, and I went up 5. And now I'm coming down 6. So I know I have to come down below where I started to about here, and then over 5 more. So it's probably going to be around this point. You see how I did that? I literally look at the graph here. Vector B, so from the end of vector A is the end of vector A right here. That's vector A drawn better to scale, 2 and 5 being more reasonable than that. I go again down 6 and to the right 5, whatever vector B tells me to do. So as I travel down 6 and over 5, I'm going to end up maybe somewhere over here, and this is going to be vector B. Now, overall, if I know I came down 6, it means I'm down 1 more unit, and I'm over 5. Makes that a 5, makes that guy a 6 right there. Overall, I want to find the resultant, right? I want to find the resultant. So how far have I gone in the x direction? How far, from beginning to end, how far have I gone in the x direction? Maria? Where are you getting the 7 from, so we're all clear? Yeah, the x components summed together. Because these components are both acting to the right. So I know that it's to the right, it means sum them. So this x directional is 7. God bless you. When I draw the resultant, though, I can see the resultant there in blue. How would I draw the triangle for this resultant? For the resultant vector in blue, how would I draw the triangle? Because Maria told us the answer is 7 for the overall x component. Where would that show up? how would I draw the triangle?
I think you would draw it below.
Tell me where to start. So let me start here.
Point below the first point.
Okay, so go down from the first point and then?
To there. Yeah.
Very good. Everybody see what Chris is saying here? Start at the first point and think about the path you would take to get there. I would go down and over or go over and down. Either way is fine. Again, down and over or over and down. Hypothetically here, because I want theta, which is measured with respect to the horizontal, it's better to go over and down actually, because then this would be theta here. So for the sake of this problem, what I will do is I'll show you with the dashed line to the right and then down. And as Maria mentioned, to the right, the number is 7 right there. That is the length of the triangle, or the base of the blue triangle is 7. What's the height of the blue triangle going to be? What is the height going to be of this blue triangle? What do you think, Sarah? Just 1. How come, Sarah? Yeah, exactly. This triangle goes up 5, and then this one comes back down how far? 6. So again, for this vector here, over 2, up 5. Then for this vector was over 5, and then down 6. So because the first vector, I ended up going up 5. The second vector, I went down 6. Up 5 and down 6 yields down 1. Okay, again, go up 5 and then go down 6. I end up 1 below where I started, which is where she's getting the 1 from. So if I want to find the result in R for this problem specifically, I need to visualize or extract the blue triangle. The blue triangle is what I'm looking for. I'm looking for the result in R, which is really the hypotenuse. 7 squared is 49, plus 1 is 50. R is going to be the square root of 50. Whatever that turns out to be as a decimal. A little bit, very slightly more than 7, not much. How do I find the angle? How would I find the angle? What trig ratio do I have been using for the angle? When I'm looking for the angle, we've been using only 1 over and over. Very good. So theta turns out to be the tangent inverse of opposite over adjacent. Where does that come from? It comes from my trig ratio. Tangent is equal to opposite over adjacent. That would be 1 over 7. So it would be the tangent inverse of 1/7. Where does that come from if we're not sure? Right here. It's hard to see it. That's the angle theta. The angle between the vector and the x-axis itself. That's the angle theta. Peter?
But are we not supposed to solve like algebra or that?
Well, at this point, how else can you do it? So the graphical approach allows you to not have to worry about using sine and cosine like you do at the table, right? You can just count.
Okay.
But if you're actually trying to find the angle theta or find the length of the resultant, you have to use Pythagorean theorem or tangent. You have to use those two. Remember, whenever you're finding resultant, this is how you get the length, this is how you get the angle always. So depending on what if the problem says just find the length, then all you need is Pythagorean theorem. If it says just find the angle, all you need is theta. But if it says to find the overall resultant, you need both of them. So you are using some algebraic means, but much less than what we did when having used sine and cosine, because we were able to count instead. Okay, both are reasonable as far as the test is concerned. It's always tan inverse of y over x. Always. Every time. It's never going to not be that. Like, you could always look for theta, but it's always going to turn out to be that value. Now, Maria, the only thing to remember is that although the overall y value was -1 because we came down, right? Notice I'm not using -1 here. I'm using 1 over 7. I still consider it to be a triangle where all lengths of a triangle are positive, so I'm looking at the positive length. My answer for this would be written as the following. I would write R as a vector equals, what is square root 50? Is it 7.1? Is it even there? 7.07? Thank you. That's the vector at, what is the tangent inverse of 1/7 become? 8.3? 30? 1/3. And what do I write as a directional? Northeast, northwest, southeast, southwest. And just look at the beginning and follow the blue path. Is that northeast, northwest, southwest, or southeast? Just literally follow the directional. Alexa, what do you got? Southeast. Okay, again, I'm going east, and then I'm going south of that. I'm going east, 7 units, and then south, 1 unit. So it's got to be southeast. Yes? Yep. So this comes out to be approximately 8.13. Okay? And if you're not getting this right now, and you're trying it over and over, it means you're not on the right mode. I've said it many times, and I keep saying it. People keep forgetting. Hit mode and put it to degree mode, not radian mode on your calculator. Okay, so if you're given a word problem, my recommendation is to start with drawing it so you can see it, but I would probably jump right into the table method, because if it's a word problem, it's not going to be a graphical approach. So this is a graphical approach where we like counted over and counted the boxes, but if it's a word problem, it'll tell you at an angle. So if you're given a word problem, you have to visualize. So for example, we won't go through the whole process, but we'll do the starting. Right, let's do like an example. Have starting points. So let's say a person walks 12 miles at an angle of 20 degrees southeast. Then the person walks 3 miles west. Then the person walks 7 miles northwest. I don't even need to draw this to do it. Northwest at an angle. Geez, I shouldn't just say northwest. Let's say at 45 degrees northwest. I don't even have to draw this as a diagram if I don't want to. But if you want to get an idea of what it looks like to visualize, the first one starts southeast, so start here. Southeast means go east and then go south. So there's the first vector. There's the angle of 20 degrees. There's the length of 12. Then from where I ended the first vector, start the next vector. 3 miles west. Which way is west? Left. So let's just go back 3. Then from where I end off that vector, go to the next one. 7 miles northwest. Which way is northwest? Right? Northwest. So now I'm going to track this one up and to the left for a length of 7 and an angle of 45 degrees. It's hard to see this. Okay, but there's my ending point. That's how I would visualize this. This length right here is 7. This length over here was 12. The 12 is associated with the first vector. So from start to end, it would look like I would end up going southwest. Right? Yeah. Southwest is probably going to be the resultant. Because it looks like, based on my diagram, that that's the resultant right there. I don't know for sure, though. And clearly, my 7 and 12 are not drawn to scale. Like the vector length 12 should be almost twice 7, and it's not, clearly. So this is not drawn well to scale. So that's why I don't want the figures to dissuade you from your answer, or disagree with your answer. So what I would do is probably jump right into the table approach for this. Okay, so the table approach would simply be x and y. Vector A, vector B, vector C, and the question of what is the result. A, B, and C. How come there's A, B, and C in this problem? How come there's A, B, and C? There's 3 vectors to start with. Okay? Answer a question. Go.
So the 12, would that be the angle or the length of
12 is the length of the first vector, because this is given as a length, this is given as the angle. So this is 12 right there, if that makes it more clear, on the actual length itself.
What's the number like between the y or the x-axis and like the third vector?
That's a 45, indicating the angle of 45 degrees right there, and that's a 7 for the length of that vector right there. So when I'm taking this approach, the easiest way to look is to look at your directionals. The first vector goes which way? Give me up, down, left, right. A combination possibly, right? Because it might do more than one. The first vector, which way does it go, Maria? The first vector, start here. Just follow the dashed line. Which way does it go? Okay, this way first. I would just follow the line, but so to the right and then?
East and then down south.
South, which is where southeast comes from, right? So east is which way in the x? Positive or negative? Which way is east? Everybody. Yeah, it's positive. So let's start by putting a positive here. But in the y direction, aren't I going south? Which is negative in the y. So let's put a negative in the y direction. We're going to do these all with positives and negatives, then we'll fill in the numbers after to make it better. In the next part for B, vector B is only going west. What does west mean?
Negative.
In the?
X.
And what about the Y?
0.
Good. Very good, Peter. There's no Y displacement when you go west. If you only walk to the left, all 3 are left. So I can already fill that in. I know that that's going to be 3 units left. That's the only one I really know. The other ones I have to use cosines and sines still. For vector C, take a look at this. It goes up and then left. So what are my signs going to be here? It goes up and it goes left. Somebody else. I've seen the same hands for the most part. Isabel, again.
So like positive in the Y.
Good.
And then negative in the X.
Well done. Very good. So positive here and negative here. So my signs are all good now at this point. I've got my signs down correct. Now all you have to do is use that same formula over and over. Vector length, cosine theta for x's. Vector length, sine theta for the y's. God bless you. I don't need to worry about vector B because it's already done. So what's the vector length for vector A? Physically, what is the length of it?
Could you repeat the vector line?
So this is always vector length cosine theta for all of these, and this is vector length sine theta for all of these. Okay, that's what we derived in the 4142 notes. What is the vector length for vector A? What is its length then? 12. So I know it's going to be 12 for both of these to start. For the x component, we said to use cosine theta. For the y component, we're going to use sine theta. But the question is, what's theta? Well, just forget the diagram. Forget the diagram. Look at the top. What's theta for vector A, the first theta? What is it? It's 20 degrees. So it's got to be 20. So you don't need the diagram is what I'm saying for this. So if you want to just cover up the diagram in your mind right now, don't use it if it helps. Just use the numbers on the top. The negative 3 and 0, do I have to change those at all? Do I have to add cosines and sines to this? Why not? Why don't I have to add cosine theta and sine theta here? What's the rationale? Catherine? Good. It's only aimed in one direction. Only the x or only the y. It's not in both directions there. And so all the girls just go like grin on that one direction. As soon as you say things like that, it just makes people think. 7 is the vector length for the third one. 45 is the angle. So you're going to do the exact same thing as this. Except where you see a 12, you're going to put a vector length of 7. Where you see 20 degrees, you're going to put an angle of 45. So this is 7 cos 45. 7 sine 45. Now, before I go on any further, the graphical approach we just took gave us, by counting boxes, these numbers right here. This table of values, literally, this table of values was filled in with the graphical approach that we took a little while ago. Okay, that's the reason we did that. But this is like the x component, meaning it's like the length here. This right here is the y component. That's this drop right here. Then this negative 3 right here is shown right here. After that, this negative 7x, that negative 7 cosine 45, that's this length right here. And then finally, the positive 7 sine 45 is this height right here. So my goal is to figure out this overall value and this overall value by summing across and summing across. So what do I get when I sum across in the x? What do I get when I sum across in the x? What's my number turn out to be? Chris?
3.33.
3.33?
Yeah.
And in the y?
0.85.
Can somebody verify these? Because this is why I'm saying like the diagram doesn't always tell you the truth. Like this does not agree with my diagram at all, the answers. That's why I'm just saying people to verify this. It probably is right mathematically. The diagram is probably not right. Are the numbers correct? I saw Isabella say yes. Yes, ladies? We all? Okay. So these numbers are correct, which means this is kind of wild. Instead of going southwest in the end, like the gold arrow is showing, we end up going to the right and up, which is northeast. So these arrows are really not drawn to scale well at all. Because 20 degrees would be a much smaller angle, so I guess the first one should have been at a much less of an angle. If that's 12, then 3 would be very, very short actually. And then 7 at angle 45 would probably come back to look like that. So this is actually my real correct vector. In green, that would be my real resulting. Do you see how what I'm saying makes sense? Like this was not drawn to scale. The 12 and 7 are not proportional. The 3 is not really correct. So if I were to draw it to scale, it probably looks more like what I show you there. So as a result, if we want to figure out what the resultant vector R is, we need to create the triangle there. And there's my little triangle right there. I'll zoom in so you can see that better. Okay, that's my little triangle right there. So the Rx component that was 3.33, right? The 3.33 in this case is corresponding to this little length right here. And the 0 point whatever right here was 0.85, I think. Yeah, 0.85 corresponds to the height right here. Okay? Again, once you get these numbers, you'd have the triangles. You can get the angle theta, which is missing right there. There's the angle theta, and there's the resultant vector r. So if you want to, not to confuse you, don't draw the original diagram. Okay, that might confuse you more than it might help you if it's not drawn to scale. I do have to move on, though. We got to get to chapter 3 stuff, so I'm going to continue with that. So I'll give you a minute for those that are still writing stuff down to write. Well, let's begin chapter 3 and talk about what we did, because there's a lot in chapter 3. This is only like a third of your test. Chapter 3 is 2/3 of your test. Okay, we had more emphasis on chapter 3. This was a much shorter lesson. So chapter 3, we talked about the concept of acceleration. That was the whole idea of chapter 3. Okay, and acceleration is only occurring when what changes? Acceleration occurs when something changes. Yeah, the velocity of an object. So the definition of acceleration, if you recall, let me use black, sorry. The definition is the change in velocity with respect to time. Okay, delta V over t. I use delta t, but then remember I kept dropping the delta, so don't worry much about the delta t. But delta V has to be written as delta because for V it means final minus initial. And you have two different velocities. If I told you the change in velocity and not told you final and not told you initial, and I said the change in velocity is 10 meters per second, then you can just put that right here. Over a time period of 2 seconds, how much is the acceleration? Boom, you're done. But that would be if you were given the change in velocity as 10. That's being told that you go from, say, 5 to 15. That's a change in 10. Or 2 to 12 is a change of 10. I'm giving you the change in that case. But in reality, remember please that this can really be written as the following. Okay, that's really the way we want to perceive this, as final minus initial. If you're given final and you're given initial, just plug them in. Or maybe you're not given final, or you're not given initial, and you're given the other 3 variables. So in this chapter, we talked about the big 3, right? Those formulas. And those formulas, you don't have to memorize them. They're on your formula sheet. There's the first one, which, by the way, remember, is the same exact thing as this formula. Those are interchangeable. Those are the exact same formulas. You're just rearranging them. That's all you're doing. The second formula, and the third formula. So those were our big 3. I have to recognize that if I'm not given something, I'm probably not going to use that formula unless needed elsewhere. For example, if I'm not given anything about time in the problem, which formula am I most likely going to use automatically? Chris? Yeah, second, because it doesn't have time, right? If I'm not asked for time, I'm not given time. Therefore, I'm not going to try and solve for t or plug in for t. Only the middle formula doesn't involve t. That's the only one that doesn't have it there. So recognize what you're given and what your desired variables are in order to help you to choose the correct equation of motion. These are the equations of motion.
On one of our homework questions, I don't know if it was a problem set or like one from a while ago.
Okay.
It said solve for VI.
Okay.
And there's no formula to solve for VI, so which one should you do?
Well, in that case, you have to pick what you're given in that case. So, like, if I'm given time, acceleration, and VF, I would probably use this to solve for VI by moving this quantity over here. Remember how I could, instead of this is being added, right? I could just subtract AT on both sides, and that gives you VI. Or here I can find vi if I do displacement, acceleration, and final velocity by moving 2ax, the whole thing, move it over, and then to get rid of the square root both sides. Technically, we get vi here also by moving this whole term over by subtraction and then divide by time to get vi. So it really depends on the context of the problem. Okay, but when the problem says to solve for another given variable or another unknown, you can plug in numbers first if it helps you. But I've been recommending solving with all variables. It's up to you to choose which way you want to take your problem. Okay, if you find it simpler to plug in numbers first and then solve, by all means, plug in numbers first and then solve. I'd rather not make a mistake with all the variables that are working here. Okay? M and then Sarah.
For the problems with A is equal to negative 9.81, are there any words, like in a word problem that would let us know that would A is represents?
Okay, yeah, so here's your indicating factor. That's a good question. A is negative 9.81 when an object is traveling vertically. That's it, when it's traveling vertically. In the next chapter, we're going to see what happens if it's traveling at an angle. That's where vectors come into play. But right now, vertical motion is when A is negative 9.81. If it's horizontal motion, either you're finding acceleration, maybe the brakes, acceleration, or deceleration, or you're given something about the acceleration being like 3 meters per second squared. So you would be told the acceleration, or you'd be searching for it if it's horizontal motion. Okay? Great question. Sarah.
For the second and third formula, does x stand for distance?
Displacement. And if it's horizontal, we call it x. If it's vertical displacement, or the problem is vertical motion, what are we talking about instead of x then? Just y, yeah. So replace this and this with the variable y, and it's the same exact equations, right? The equations do not change in the vertical and horizontal direction. It's just a function of, you know what, which of these are we really going to use? Okay, which one of the three work for us? Just plug in the y where you see an x. Let's go over some real quick theoretical stuff that we need to know, right? So let's talk in the beginning of this section, we talked about horizontal motion. If an object starts from rest, what do you know? These are key words. You might probably want to write these phrases down, right? Because this is how you dissect the word problem. Alex, starts from rest.
The velocity initial is 0.
Good. Initial velocity is 0. So starting from rest, you write down right away, vi equals 0. What if the problem says it comes to rest, or it comes to a stop, or it comes to a halt at the very end? What do we then know, Sarah? Good. Then Vf is 0 in that case. That's horizontal motion that we're talking about right now, okay? Horizontal motion. If you hear the phrase, the object's velocity increases, what can you automatically conclude? If you hear the phrase, the object's velocity increases, you can conclude what? Very good. Well done, Catherine. You must have acceleration, and even better, she added on, it's positive acceleration. What if it said the velocity decreases then? Negative acceleration. What if I said the velocity is constant? The velocity is constant. Therefore, good. There is no acceleration. Acceleration is 0. That goes back to my graphs. And we're going to look at graphs with about 2 minutes left. Remind me to look at graphs. Now, that's horizontal motion that we've been focusing on for the last 2 or 3 minutes there. Vertical motion obeys the same laws, except there's some little tidbits along the way that we need to remember. First, when I toss an object like we did with it was like a pool ball, billiards, right? Pool ball. When I toss this object up and down, what happens at the very top? At the very top, what happens? It stops for an instant, right? It's got to stop. It's got positive velocity, then it stops, and then what kind of velocity? Negative, 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 more and more negative. The whole time, though, as Em asked earlier, what's the acceleration? If it's vertical motion, the acceleration is always what number again? Negative 9.81. It doesn't matter if I throw it like this, at this moment, at the top, even when it stopped, there's still acceleration, and it's still negative 9.81. The entire time it's in vertical motion, the acceleration is always negative 9.81. Now, we also talked about symmetry in problems. If I throw an object upward and it takes 5 seconds to get to the top, what can you deduce? Assuming no air resistance.
That on its way down, it will be the exact same, but negative velocity.
velocity. So for time, we can deduce it's just 5 seconds for now. So 5 seconds up means 5 seconds down, assuming you start and end at the same location. The second part, which Chris kind of gave a little hint already, if I throw it upward with a velocity of 20, it gets less and less velocity until the top. It's 0 velocity, then -1, -2, -3, -4, all the way until it gets to -20. The same velocity you throw it with is the same velocity it will land with, assuming no air resistance. That's the key to these problems. As soon as there's air resistance, the symmetry of the problem, that symmetry that we see, will not exist. Okay, it will not exist. If you're given a problem that asks you to find the time it takes to get to a certain height, right? A certain height, given an initial velocity, you might have to use a quadratic, and you did one of these. It was actually the last example in the notes that day, and if you recall, I told you guys to take notes on your own and watch it yourself, so I'm hoping you did it. You should definitely be ready to be able to do that on the test, be able to solve a quadratic. Whether that's using the quadratic formula, do all the work by hand. If you program the quadratic program, like I told you, that's under documents and handouts. The whole worksheet, you know how to do that. It's on documents and handouts. If you program it in your calculator, you can just tell the calculator A, B, and C, and you get the answer. Or you can solve it by looking at the graph and finding the x-intercepts. But the idea here is what I'm saying is that, you know what, maybe you're given the x value, given VI, given A. The problem is you got to find T, and it's in 2 spots. So that makes it a quadratic. So let's say we're trying to figure out when an object gets to a height of 12 meters, if the initial velocity was 20 meters per second, this is what the equation becomes. Right? And then the problem is that T is in 2 spots, so you can't solve for T. It's a quadratic by nature. And what would this quadratic look like if I make it nicer? 1/2 times -9.81 is -4.905. And that's going to be T squared. The 20T is positive still. And then if I want to move the 12 over here, I have to subtract it. So that becomes a -12. And then there's your quadratic you would have to solve. Okay, if you're really not sure how to solve a quadratic, you need to do your homework. Okay, you need to do your own work to get that value and figure that out. Yeah.
Is there actually already a program on the calculator that's...
If there is one, some of the newer ones have quadratic programs already written. But if you have an 83 or an 84, like the original ones, you're not going to have a program on there already written there. Okay, but you can use the graphing feature to do it. You can also just type in the program. The program is on documents and handouts if you want to use it. That's up to you to put the time in. No, I'm not going to do it for you. Okay, so be able to solve something like this. Let's go to graphs. Yes, Sarah? Yeah, hypothetically, the problem says, an object is thrown with initial velocity of 20 meters per second. Find the time it takes to get to a height of 12 meters. The height is 12. That's your x, or in this case, y. VI is 20. Acceleration is always this number whenever it's vertical motion. T is the only unknown. You would solve for T. Okay, but again, with a quadratic. You cannot solve for T algebraically. You got to use the quadratic formula. I want to get to graphs. Okay, we have a couple minutes left real quick. So let's get to graphs. We've looked at 2 types of graphs now. Mind you, by the way, like I said, the other class I went into a lot of details with graphs. So if I run out of time, please look at their video. We've looked at position versus time, and we've looked at velocity versus time. We've described these as a function of each other also. We've done this in the lab. We've done this with the picket fence. With the picket fence, we only graphed the velocity curve, and then we looked at the displacement curve and saw that parabolic nature because of the 1/2 AT squared in the formula. Whereas with this one, we didn't see that as much. But what I want you to point out is that they're different, right? So if I were to look at a graph that looked like this, excuse me. Okay, if that's the position graph, and I wanted to think about what that means, I can write a story. Give me like a minute or 2. The story could say the following. The object's position starts away from the origin. The position increases, and then the position remains constant. Then the position decreases, and then it remains constant. I could also write the same story and say this. Because its position is increasing, the velocity is positive. Because the position is now staying the same, the velocity is 0. Because the position is decreasing, now the velocity is negative. And then here the velocity is 0. So if I were to graph this, there would be positive velocity, no velocity, negative velocity, no velocity. So my graph of this would look like the following. I'd have positive velocity, then I'd decrease real quick to no velocity. That's the middle region here. Then the negative velocity shows that velocity is below the axis. That's negative velocity. And then, again, when it's not moving here, right, position is steady, there's no velocity in the last piece. So understanding the difference between these graphs and how to relate them to one another is also an important aspect of this test. Okay, and we saw this a lot in the labs, in lab 2 and in the lab that I didn't have you do a write-up for with the picket fence. We fit, if you recall, we fit a velocity graph and found the acceleration as the slope of that. So to conclude, the slope of this graph is really the velocity, and the slope on this graph is the acceleration. And the reason I can conclude that is because this slope is positive. That means that there was a positive velocity. This slope here was 0. That's why there was 0 velocity. This slope was negative. That's why the velocity was below the axis, meaning negative. This slope is 0, 0 velocity. From this graph, I can say that the acceleration is some constant, whatever the slope is. I'm sorry. The slope here would be 0. What am I saying? So the acceleration is 0 here. Then you've got a negative acceleration, making it stop. Then the acceleration is 0. Then you've got more negative acceleration, making the object go with negative velocity. Then you've got positive acceleration, which is actually slowing it down, which bringing it to 0 acceleration at the end. This is a little bit tricky because these lines are at weird angles, each of them. Trying to think of anything last minute with graph that I could ask you that you want to know. Be able to interpret both these graphs. That's what I'm getting at. Okay, if you're given a position graph, recognize that it's position. How do you recognize that? Look at the axis labels. Okay, you can go if you want to go at this point.
So what does it all the way bottom line represent for acceleration?
This right here, that dot?
No. Like the lowest bottom point. That one, yeah.
That?
What is that? Yeah.
So
What is that
what I'm
dot?
seeing here is that this region is coming from this part right here. See how the slope of this is negative? That's why the velocity is below the axis.
Right.
But see how the slope of this is steady? It means that I'm walking in the negative direction with a constant velocity. That's why this was constant, right? Because this is a constant velocity here, Peter, this bottom, it means that the acceleration there in that region has to be 0. It's literally, this graph is me doing the following. Positive velocity, 0 velocity. Negative velocity, 0 velocity. I just literally enacted this. Positive velocity, 0 velocity, negative velocity, 0 velocity. It's the same thing as this. Positive velocity means positive slope. 0 velocity, 0 slope. Negative velocity, negative slope. 0 velocity, 0 slope. So the slopes of these are what are giving me these over here. Okay, very similar to your second lab. Maria.
Wait, what is that?
Yeah, but technically, it would be impossible to stop on a dime. You ever hear that phrase, stop on a dime? It means like you stop instantaneously. Everything needs to break over a certain time period. So technically speaking, Maria, there is a little slant to all these lines. In your lab, I think you drew it pretty vertical, it's fine. But there's technically always a slant to all those lines. It's a very minimal slant, but that slant is showing that you're going from some velocity to no, like how would I just go to no velocity? Like, ready? Like I could just stop, but I kind of slow down there in the end. I have to see it, right? It's almost impossible to pick up, but you have to slow down. This quick, steep line is showing a lot of braking force. That's me literally stopping like that. That's what the acceleration, meaning negative acceleration, slowing me down really is. Okay, so there is a little slope to those lines. There was another hand that was up though besides mine. Okay, if you have any other questions, you can hang for another I can go 10 more minutes or so until about 2:45, but I got to meet your parents at 3. So I need time to just drink a little bit of water and catch my breath before I have parent-teacher conferences. I'm excited to see your parents. I mean, for the most part in my class, I've never had any bad experiences with parents because for the most part, every parent sees all the stuff that we do in class online. They know what's going on, so there's nothing unaware of them. So I'm hoping I do get to see a lot of your parents today if they do come. You can hang if you want, you can go if you want. Obviously, it's up to you guys, but I'll take no questions.
Do those two correspond with each other?
They do. They absolutely
Now,
do.
I'm still on team.
So this is a positive slope, right?
Yeah.
That's represented here with a positive velocity.
Sure. Yes.
This is a slope
but
of
no
0.
acceleration.
Slope of 0 means no velocity. Because think about it, this is position. This means I'm moving away at a steady pace, which is a constant velocity.
This extra 2 is like just added on though, right?
What, this little piece right here?
Those-
and this piece?
those extra 2
and this
pieces?
Piece? Yeah, this piece, and this piece is just a little extra stuff that I added.
Oh, okay.
So this corresponds to this. 0 slope is 0 velocity. Negative slope is negative velocity. 0 slope is 0 velocity. Do you see how there's 1, 2, 3, 4? 1. You're welcome, guys. Have a good day. I'll see you tomorrow. 1, 2, 3, and 4.
Oh, so this like can't correspond with that because this is measuring acceleration and this is not. I mean, you can't like have many.
Yeah, that's the
you know?
issue. We really don't know the context of this as much because I don't know. Chris, did I walk and slow down eventually? Did I walk and stop suddenly? So I don't really know too much about those in between. So we can just connect them with lines for now, showing that there's suddenly positive velocity and then a drop in velocity to 0. How can that happen? How can you go from positive velocity to no velocity? You have to have negative acceleration.
Thank you.
Well, you're welcome. The slope of this line is acceleration. I'll see you tomorrow, Marco. The slope of this line is acceleration, and the slope of that line is negative here. That's why it's negative acceleration. I didn't ask for this. Shoot. How many people turned it in?
I don't know. I did a physical.
Physical copy. See if anyone else
Oh,
did
you want
physical.
right? You want a physical copy for that, or?
No, electronic's
Okay,
fine,
okay,
but
alright.
physical copies need to be turned in because I can't see them if not. And I need to turn back some of the older ones.
Will that graphing?
Actually, Ken, you're still here, right? Steve, here, it's yours too. Steve, I know. This is your problem set number 1, just so you can see it at least. Hard copies.
All right. Thank you.
And these are yours.
Is
Homework
the
set.
graphing on test like the graphing that you just showed us today?
Just that right now? Just
No, I
that?
mean like
the graphical
define
approach?
vector. Yeah.
Yeah, I showed you
Or
that
is
at the
that just
beginning
a
of
method?
4.1. It's the whole beginning of 4.1. Go back and look at 4.1.
Is it just a method, or do we have to use it?
You're going to be asked to do one graphically and one algebraically.
All right.
So we'll go back to 4.1, 4.2, look at the beginning of that. That's where we went all the graphical stuff.
Oh,
was
that's
covered.
what that was.
Remember
Okay,
with
yeah,
the grid lines and stuff?
Mhm.
Yes.
Okay, so you answered my question, but also that if like you give us that graph, we would expect us to.
I would expect you to be able to relate this to it, for sure. So I could give you either one. I could give you this graph and you can be able to draw this. I can give you this, you can draw this. Or I can give you this and tell me to write a story. I can write a story and tell you to draw a graph. You know what I mean?
Yeah.
So there's so many ways.
When you, so like I understand, like which one it corresponds to, but we have
Okay.
to like mark it, say like this, like that line.
Sure. Like this slope of this line is really the y value of this line. The slope of this, which is 0, is a y value of 0. This slope is negative. This has a y value that's negative. So yes, they correspond accordingly. It's 1, 1.
Like mark, like so we show you that.
It depends on what I ask. I'm not going to answer that either way, but you should be able to do that. Yes, you should absolutely be able to do that.
Okay, thank you.
You're welcome. Yeah, by all means. I'll hang till 2:45, but then I just need a little bit of time to breathe. So, yeah.
Like once you're using